Welcome to this lecture where we're going to talk about how to use our analysis tools to get a T of n for a particular bit of code. We're going to show how to move from code to T of n by labeling every fixed time operation that occurs in the code, counting all those operations very carefully, and then applying big O to get a simpler upper bound for the T of n that we have calculated. So before we can apply big O to get a simple upper bound, we have to have the T of n. And T of n comes from looking carefully at the code or thinking carefully about what the code might do and counting all the steps carefully. Now, for each step in the code, we have to know how long it takes. So we're going to label our fixed time steps. You might look at these three different statements, I++, C out, left shift I times 3 plus j, quantity times k. How much time does each of these take? I don't know. Maybe a cycle here, maybe a few cycles here, maybe a few cycles here, CPU cycles. We don't know how much time these take, but each of them is fixed time. Each of them is a step, because if I have an integer, a C++ 32-bit integer or 64-bit integer, incrementing that integer takes a fixed amount of time, right? Doing it once, adding 1 to it. Printing out an integer takes a fixed amount of time because a 32-bit or 64-bit integer has at most, something like 9 or 18 digits that it could print. Okay, and doing some math with some integers has at most, we're doing 3 operations here. That's 3 times the cost of any one of those operations. Now, I hope you would agree with me that the cost of doing I++ is fixed time, and so is the cost to print out I, but the cost of those two things are not the same. In other words, these are both fixed time, but they're not the same. So what we're going to do, for the purposes of thinking about this carefully and critically, we're going to label each of these with a cost like C1, C2, and C3. These are constant coefficients, and these constant coefficients will say this is C1, C2, and C3. So how much time does this step take? I don't know, but I'm going to call it C1, and that's a constant, which represents a number of steps, right? How much time does it take to print I? I don't know, but I'm going to call it C2, which represents a constant amount of steps. And how much time does it take to do this calculation? C3. And C1, C2, and C3 may be the same, they may be different, but it represents our belief that these are constants, but we don't know exactly what their values are. All right, all that aside, let's launch into our first example. Suppose I have an input of an integer n, where here n represents the size that I want to print, right? The value that I want to print up to, and I'm going to print up to that value from I equals 0 up to, but not including n, and I'm going to increment I every time, right? So what I've done here is I've laid out the code in kind of this peculiar fashion. I've separated I equals 0 from I less than n from I++, because each of these are different separate steps. And the cost of allocating I and setting equal to 0 is C1. I've just called it that. And the cost of doing this comparison is C2. And again, I've just called it that. And the cost of incrementing I is C3. I've just called it that. And the cost of printing out I and an endl is C4. Okay. So now our job is, if these are the cost of each of these occurring once, we need to figure out how many times each of these statements, these steps, occur. How many times are we going to allocate I and set it equal to 0? Well, that's going to happen one time, only one time, right? How many times are we going to compare I with n? Well, think carefully about this. I starts at 0, I goes up to n minus 1, and then once it gets to n, then the loop stops. So the value of our I starts at 0 and goes up to n, at which point the loop stops. So there are going to be n minus 1, I'm sorry, I is going to have values 0 through n minus 1, where this comparison is false, and then one more comparison where it's, I is going to have n comparisons where this comparison is true, and then one more comparison where it is false and the loop stops. Okay, so this actually happens n times plus 1 for that last comparison, which causes it to kick out of the loop. I++, which costs C3, will happen n times. And we can think easily about this because I starts at 0, I ends when I is equal to n. How many times do I need to increment I to get from 0 to n? Well, I have to increment it n times. And we're going to print from 0 up to n minus 1. That's also n times. Okay, so what we've done here is we've labeled all of the costs for the purposes of being careful. We've also counted how many times each of these steps occur. And we can associate that the total cost of this step is C1 times 1. The total cost of all the executions of this step are C2 times quantity n plus 1, C3 times n, and C4 times n. So that's what we end up with. Okay, we have C1 times 1, C2 times quantity n plus 1, C3 times n, and C4 times n. Now, if I were to take this and apply the rules of big O, for simplifying, we can eliminate the low order terms. Well, this is a low order term. Essentially, this is a low order term, that plus 1. And then I'm left with something like C2 plus C3 plus C4 quantity times n. Now, these are constant coefficients, which I can eliminate, and I'm left with just n. So T of n is equal to big O of n, okay? But what I want to emphasize here is that we labeled each of the costs individually, we counted them carefully, and then we used that to come up with a very carefully defined T of n, okay? And before we could get to big O, we needed to write down this T of n very carefully. Let's look at a second example, which is simpler, actually. Suppose we were going to print a single number, that number is n. Notice that all it does is it prints n and an endel, and that costs C1, and that happens one time, right? So the cost of this is C1 times 1, right? And if we eliminate the constant coefficient here, we're not going to eliminate that 1, but we eliminate C1, and so we say this is constant time. It's big O of 1, constant time. Let's look at a third example, which is more complicated now. Suppose we're given an array, A, and the length of that array, N, and we're going to bubble sort A, okay? Again, we've separated this into each of the discrete steps that it will take. We've labeled them C1 through C8, and let's count how many times each of these occur. We're going to allocate this one time. We're going to make this comparison, like we saw before, n plus 1 times, because I is going to start at 0, it's going to finish at n, and we're going to make a comparison for each of those values, 0 through n. So we're going to make n plus 1 comparisons. I++ is going to happen n times because we have to move from 0 to n, and we have to increment I n times to do that. Now, this inner loop depends on the outer loop, so this allocation and assignment is not going to happen once. This is actually going to happen n times. Why does it happen n times? Because the outer loop causes it to happen n times. This comparison is going to happen n times due to the outer loop times n minus 1 times, sorry, not n minus 1, times n times for the inner loop. So this n right here is for the outer loop. This n right here is how many times we actually compare j with n minus 1. And j starts at 0, j finishes at n minus 1. That means that we're going to compare for 0, 1, 2, 3, up to n minus 1. There are n comparisons there, so we have n times n. Now, we have to increment j how many times? Well, we're moving from j equals 0 to n minus 1, which means we increment j n minus 1 times, and we're doing that n times, I should put this over here for consistency, n times for the outer loop, right? The outer loop makes us do this n times, and the inner loop does it n minus 1 times. And the answers for both of these, or the counts for both of these, are similarly going to be n times n minus 1 and n times n minus 1, because they are going to happen just as many times as we increment this loop. Now you might wonder, but what if this if statement isn't always true? That's okay. The swap might not happen as many as n times n minus 1 times, but remember, we're thinking about the worst case here. And in the worst case, it is possible that every time we make a comparison, we also have to make a swap, okay? So we're thinking worst case here. So after all of this, we're going to multiply, to get our T of n, we multiply C1 times 1, C2 times quantity n plus 1, and so on to get this, okay? So here we've written in all the times like we did before, and we have T of n equals C1 times 1, C2 times quantity n plus 1, etc. And we're going to have some n squared terms in here, 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 and here. If we drop the low order terms are those involving just n, for example, and just the constants, and we group like terms and we drop the constant coefficients, eventually we'll get to T of n is equal to big O of n squared. Okay, so this bubble sort algorithm, as we've written it, is upper bounded by n squared. It's equal to big O of n squared. Now, some of that was not as clear. Like if getting some of these numbers over here was not as clear, I'd recommend doing more practice. And one of the ways I recommend practicing is making a table of values for different values of I. For example, how many times does this happen? And how many times does this happen? And how many times does this happen? I'll make a separate worksheet or activity for that because I don't want to put that in this video. But I hope this has been helpful for you to see how we get to T of n.